Hello, thank you for watching this video. So my name is Keir Rogers. I'm a postdoc at the University of Toronto, and I'm presenting searching for ultralight axion dark matter in BOSS galaxy clustering, and I will discuss some implications of the search for dark matter for the S8 tension. So in this work, we're trying to learn something about the fundamental properties of the dark matter using observations of the large-scale structure, in particular, the clustering of galaxies in the Baryon Oscillation Spectroscopic Survey. And this sits within the context that the traditionally preferred candidate for the dark matter, the weakly interacting massive particle, the WIMP, has not been detected at high energy colliders or through direct or indirect detection so far. And that has motivated a big shift to consider well-motivated theoretical alternatives to the WIMP and new experimental approaches to detect these dark matter models. And so this slide is a very top-down schematic view of the dark matter model space, where in particular, we can consider dark matter candidates that are lighter than the massive particle that constitutes the WIMP. And in particular, if you have particles which are lighter than around 10 to the minus 18 electron volts, by the uncertainty principle, their wavelength becomes astrophysically large. And so the large scale structure is a very good probe of what we call ultralight axion dark matter, these very light particles, which can behave like dark matter today, or if they're below this around 10 to the minus 27 eV mass scale, in fact, are behaving like dark energy for part of the cosmic history before today. And I will interchangeably refer to ultralight axions or ultralight boson dark matter. And axions are a particular particle physics motivation for very light dark matter particles, which is most easily motivated in the so-called string axiverse. The idea that in string theory, you produce many different axions, each of different masses, and that one or more of these is a viable dark matter candidate. And in fact, when you calculate the spectrum of masses of stringy axions for different string theory compactification scenarios, so that's what's illustrated here, you're seeing the spectrum of axion masses, where each colored line is for a different compactification in string theory, you get quite a generic outcome, which is that you get a roughly log uniform distribution of axion masses. And that means that you will consistently produce a population of ultralight particles with masses below 10 to the minus 18 electron volts, but you will also consistently produce a population of heavy axions. And from the point of view of the large scale structure, these will be indistinguishable from standard cold dark matter. And that has a very important consequence when we search for ultralight axions in cosmological data, which is that we must allow a fraction of the dark matter to look like ultralight axions, but we must allow another fraction to behave like cold dark matter and to vary these energy densities independently of each other. And so this is interesting to search for dark matter in the large scale structure. And when we do so, we must take account for consistency between the data sets that we use under a given model. And that leads us to consider the status of cosmological tensions. So in particular, what's relevant to this work is the so-called S8 tension. So S8 is this combination of sigma 8 and omega m, the matter energy density, where sigma 8 is measuring the variance in the clustering of matter when averaged over 80 megaparsec scales. And the tension arises because there's a systematic difference in the inference on its value when considering cosmic microwave background experiments. So these are the blue points at the top here, which have systematically higher values of S8 than when it is inferred from various large-scale structure experiments. So in particular, galaxy clustering and galaxy weak lensing. And one way to think about this is that the CMB is mostly measuring larger scales. And so you are more indirectly inferring the amount of clustering at 8 megaparsecs, whereas these large-scale structure probes are more directly probing smaller scales. And that suggested that if you had some sort of scale-dependent clustering arising from the nature of the dark matter relative to the cold dark matter limits, then that may be able to reconcile these high and low values of the S8. And so I will discuss that in more detail later on. So let me move on to the details of our analysis and give thanks to these excellent collaborators who all contributed to this work. So the reason that ultralight axions, particles with masses less than around 10 to the minus 18 electron volts, can be probed so well with the large-scale structure is that on scales below the de Broglie wavelength of the particle, you will have a strong suppression in the growth of structure relative to cold dark matter. So ultralight axion dark matter causes a scale-dependent suppression in the clustering of matter, and the Jeans wavelength at which suppression begins on scales at and below this wavelength is given at the top here, and I'm showing how it depends on redshift, axion energy density, and the axion mass. And so you note that as the particle gets lighter, by the uncertainty principle, that de Broglie wavelength gets larger, and so this Jeans wavelength is larger also, and then vice versa. And so we can look for the scale-dependent suppression in the linear matter power spectrum. So that's what I'm showing in the top panels, where I'm increasing the axion mass from left to right. In the bottom, I show the ratio of an axion linear matter power spectrum in ratio to the cold dark matter limit, where I'm increasing the fraction of the dark matter sitting in axions from 0% up to 8%. And you see two key effects, which is that as I increase the axion mass, the wave number of suppression gets larger. And as I increase the amount of axions, the strength of that suppression increases. So we can't observe the dark matter distribution directly, but we can trace it through the distribution of galaxies, which we observe in galaxy surveys. And that means that we need a way to model the effect of axions on the clustering of galaxies into the mildly nonlinear regime. And we approach that with a perturbative approach based on the so-called effective field theory of large-scale structure. So this is a schematic view of that model. And so what we're modeling is the multipoles of the galaxy power spectrum. So L is indexing the Legendre expansion of the anisotropic redshift space power spectrum. And we have a set of terms that account for linear order perturbations based on a Kaiser model. We include perturbative corrections up to one loop order. We have ultraviolet counter terms that account for the effects of short scale physics. Stochastic terms that account for shock noise, redshift space distortions. We also account for infrared resummation and Young opportunity distortion. And the key point here is that this model depends only on the linear matter power spectrum. So you have a bunch of free parameters that we marginalize to account for uncertainty in, for example, exactly the form of the counter terms. But in terms of physical inputs, it only comes from the linear matter power spectrum. And so we can model the effect of axions in the galaxy clustering up to mildly nonlinear scales just by accounting for their effect on the linear matter power spectrum, as you saw on the previous slide. And so this is the effect of axions on the galaxy multipoles. At the top, we have the galaxy monopole, the angle averaged component. At the bottom, we have the galaxy quadrupole. Again, increasing axion mass left to right and increasing the fraction of the dark matter in axions from 0 to 8%. So for the two leftmost panels, the scale of the suppression from the axions is on scales larger than we are modeling here. So all the power spectra are suppressed. But for 10 to the minus 26 EV, we can see this scale-dependent suppression. And we see an interesting effect in the galaxy quadrupole, where in fact, as I increase the amount of axions, I get a relative enhancement in the intermediate scales of the galaxy quadrupole. And this is arising because the galaxy quadrupole is sensitive to the fingers of God effect, where structures along the line of sight are elongated by nonlinear peculiar velocities. What happens is that in the presence of axions, the strength of overdensities is diminished. The infall of particles to that overdensity is weaker, and so that fingers of God effect is diminished. And so that suppression from fingers of God is relatively diminished, i.e. we have a relative enhancement compared to the cold dark matter case. But on much smaller scales, the overall suppression in the power overtakes from the effects of the axions. So having modeled how galaxy clustering responds to axions, we can confront this with BOSS DR12 data. We also combine this with Planck data, measurements of the cosmic microwave background. The combined constraints are shown in purple, which are always the strongest. And this is the upper limit on the physical axion energy density as a function of axion mass. And you can see that for masses at 10 to the minus 26 eV and below, the constraint is quite strong. So it has to be less than about 0.01 in terms of physical energy density. But for masses of 10 to the minus 25 electron volts and higher, these data still allow a significant fraction of the dark matter to sit in ultralight axions. So what are the implications of this for the S8 tension? So this is a triangle plot showing constraints on an extended cosmological model with additional axion energy density in the far right. And in black, you see a combination of large-scale data from Planck CMB, high-resolution CMB from Axion SPT, galaxy BO, and supernova data, and analyzed under lambda CDM. And you have the systematically higher value of S8 compared to fiducial 3x2 clustering or weak lensing analyses from KIDS and DES. And when we then analyze this large-scale data with the presence of axions, we naturally recover low values of S8. And that's because of this very strong degeneracy with the axion energy density. What that's saying is that when we have an axion, if the mass is fixed to 10 to the minus 25 electron volts, and we allow the presence of axion energy density, this predicts a scale-dependent clustering, a suppressed amount of clustering around 8 megaparsec scales. So we're still consistent with the large-scale data, but we predict suppressed amounts of clustering on the smaller scales that these 3x2 analyses are more sensitive to. So this is sort of showing our hypothesis that having a fraction of the dark matter sitting in an axion of this mass can give low S8 values. And the acid test is to then confront these galaxy clustering and galaxy weak lensing data under the axion model to see if we have consistency between these data sets under this extended model. And so I will now show you the results of confronting that with a full shape galaxy clustering in the power spectrum and the bispectrum. So as before, we're looking at the galaxy monopole, which is the blue line, the galaxy quadrupole, which is the orange. The galaxy, we now additionally use the galaxy hexadecapole, the next non-zero component of the multipole expansion. And we additionally use the statistic Q0, which is a reconstruction of the real space power spectrum. So we downweight information in the nonlinear retrospace distortion, which is hard to model to small scales. And by downweighting that information, we're able to recover a tracer of the real space power spectrum, which we are able to model more accurately to smaller scales. And so by having this additional small scale information, we become more sensitive to the scale dependent clustering of axions. And so we have a stronger test of this axion model. So the solid is a lambda CDM model, and the dotted is where we then allow 75% of the dark matter to sit in an axion of this mass. You see the scale dependent clustering. The bottom right, you see the monopole of the bispectrum, where in the dotted line, again, you see the effective a fraction of a dark matter sitting in axions, the effect is rather modest, as this is currently only measured and modeled on relatively large scales, although it may be interesting to look for axion-induced isocurvature in the bispectrum. So here is the result of confronting this extended cosmological model with axion energy density with an axion of mass 10 to the minus 25 eV. In yellow with Planck CMB data, in black the Bose galaxy multipoles, and the magenta is the combined constraints. So parameters as before, except we're additionally showing the linear order galaxy bias B1. And so the key points here is that in the presence of Bose galaxy multipoles, you get a stronger constraint on the amount of dark matter that can sit in axions. So this is saying that only about 50% of the dark matter can sit in axions of this mass. But when we then combine that with Planck information, Planck constrains the cosmological parameters very strongly. But Bose leaves enough axions that we can still exploit this degeneracy between axion energy density and S8 to get to lower values of S8 than the lambda CDM limit. And so the final piece of this is to confront this with galaxy weak lensing data to see if you have consistency between these data sets under this extended model. And I can show you preliminary results analyzing cosmic shear data from the dark energy survey, but here in the limited case where axions comprise the entirety of the dark matter. And you see, in fact, that by combining weak lensing from DES and Planck CMB, we can set a very strong lower limit on the mass of the axion when that axion comprises all the dark matter, 95% lower limit at 10 to the minus 23 electron volts. And this is now being modeled using a modified halo model. So the next step is to extend this to the mixed axion and cold dark matter case, as we considered before. So let me finish by showing a summary plot of our current state of play understanding on the allowed fraction of the energy density sitting in axions. Everything in solid is excluded. So from CMB, Bose galaxy clustering, galaxy weak lensing, and Lyman alpha forest data probing these heavier ultralight axions. But there's a lot of viable parameter space where still a significant fraction of the dark matter can sit in ultralight axions. And these are within the reach of upcoming large-scale structure experiments. So I have CMB S4 lensing in blue, a projected sensitivity, for example. So thank you for listening, and I'm looking forward to discussing at the conference.